Hi everyone. This is a video presentation of my work on conformal out-of-domain detection for specialized LLMs. This work was done as part of my internship with SRI and has been published to EMNLP 2025. So imagine you have an AI assistant which is an expert on every cookbook ever published. So if you ask it a cooking question like what's the proper technique for making a French hollandaise sauce, it will give you a very satisfying answer with all cooking related references and instructions. But if you ask it something unrelated, like how do you fix a leaky kitchen faucet, there's a chance that it might hallucinate with cooking related text because that's what it is trained to do, right? So it might say that, make a solution of white wine or use a gelatin-based sealant. This is the problem of hallucination, which we are targeting in this work, where a model, outputs plausible responses, but which are clearly wrong. And while this might be humorous in some cases like these, it can be disastrous for safety critical applications like healthcare. So imagine if you have a LLM trained on mental health and you have a mental health patient. What if the patient asks something slightly unrelated and the model hallucinates, and it hallucinates in a very dangerous way? So we need to detect these potential hallucinations in these critical scenarios. Importantly, we need to do this detection at inference time. So of course it is possible to train a classifier to detect out of domain inputs and just, prevent the model from answering if the query is out of domain, detected to be out of domain. But this is not scalable because you would need a classifier for like every possible out of domain input, right? Or you would need a very large classifier trained on every kind of possible out of domain query. So training a classifier is out of the question. And even if we don't want a classifier and we want to, train or specialize the LLM itself to detect these out of domain queries, that is not very practical because first of all, like new LLM models keep coming on so quickly. And second, more importantly, the user is usually not the one designing the models or making the training time decisions for these LLM agents. So, but the user does want to detect out of domain queries. So ideally, we want a detection method which can work on any model on any domain without making any assumptions about how that model is trained, right? So that is the problem which we are targeting in this work. And to understand what we did, let's just first go through this background concept of polysemanticity. So what it says is basically in LLMs and these any deep neural networks in general, they can store a very large number of concepts, and the number of concepts is actually far greater than the number of neurons they have in each layer. So the only way this is possible is that if each concept is represented by a group of neurons in each layer. And inherently this brings about some redundancy in the representation because if one or two neurons in that group they are missing, corrupted, or dropped out, they can be the feature can be reconstructed when it moves to the next layer by the other neurons in that group. So polysemantic networks, they are inherently a bit robust to feature perturbations like this because of polysemanticity. So can we use this idea? Can we use the polysemantic robustness to feature perturbations or tolerance to drop out as a signal for the model's confidence for any query? So we would like to answer the question like how much dropout can we introduce before breaking the model? And can the answer to this question help us detect out of domain queries? So we hypothesize that in-domain inputs, they would have a robust representation. They would have a larger number of neurons representing each concept, and thus they would have a higher dropout tolerance. And similarly, like out-of-domain inputs, they would have very brittle representations. They would have a smaller number of neurons representing each concept, so they might have a lower tolerance to dropout. So we use this technique called iterative dropout, to check to convert our hypothesis into a framework for out of domain detection. So what we do is, given a query, we ask the query to the model and we get some original response. Now over multiple iterations, we keep asking the model the same query, each time introducing a little bit more dropout than the previous iteration. And we continue this loop up to a point where we get a completely different response. So when the meaning of the response changes, we stop the loop and we record the amount of dropout we needed to introduce to get this change response, and we record it as the dropout tolerance of the model to that query. Now, from this dropout tolerance, we compute something called a non-conformity measure. The formula is given here, but basically it is a measure of how abnormal a query is. So abnormal query roughly means, out of domain query, and a normal query would mean an in-domain query. So a good non-conformity measure should be higher for out-of-domain queries, right? And we can see how if the dropout tolerance is lower for out-of-domain queries, the non-conformity measure which we propose, that will be higher. So yeah, that works out. And now what do we do with this non-conformity measure, right? We actually need to detect the out-of-domain responses or out-of-domain inputs. So we feed these non-conformity measures into this framework called ICAD, which is Inductive Conformal Anomaly Detection, which is basically a framework and a set of mathematical equations for anomaly detection. It takes as input the non-conformity measure for a query, and it predicts whether that query is in domain or out of domain. So it consists of two steps. Now, the first one is the calibration stage, where you have a small but representative set of a typical in-domain data, and you use this calibration in-domain data to calibrate the scales of ICAD. So ICAD framework now has some idea of what a typical in-domain query looks like and what is the typical dropout tolerance for these all in-domain queries. And now, given a new query, you use this, you perform the same procedure, you do iterative dropout, you compute the dropout tolerance, and then weight against all of the other elements in the calibration set, or basically like you weight against this calibrated scale of ICAD, and ICAD gives you a probability of how likely that query is to belong to an out of domain set, right? The more importantly, like ICAD provides theoretical bounds on the false alarm rate for detection of OOD inputs. So that's one very positive thing about this framework. So everything which I described earlier, that was referring to if we used dropout within one layer. But what we do in our main method is that we actually ensemble the predictions over the earlier layers, on the middle layers, and then later layers. So we perform this procedure independently for each of the layers, and then we compute multiple scales through the calibration step of ICAD, and then we weigh a new query with each of these multiple scales and then aggregate the prediction. And there are like different aggregation methods which we can use. We have experimented that in the ablation section, but basically after this aggregation we are able to generate a more robust representation or robust prediction. So this is the experimental setup. Like we experimented with a couple of medical specialized LLMs on different medical domains. We had some in-domain data sets, and then correspondingly we had some out-of-domain data sets. Of course, like there were no overlapping topics of the between the OOD and the in-domain data sets. And these were our main results. We can see that we are able to detect out of domain queries reasonably well for multiple of these model and dataset combinations. And ensembling, which is the blue curve on the top half of the graph, that actually performs much better than if we use individual layers. So our method works much better than the baselines, while also providing the theoretical guarantees shown in the bottom graph of false alarm rates. So these were some ablation studies. I mean, you can refer to the paper for more details. But yeah, to conclude, like we propose a novel conformal out-of-domain detection method using dropout tolerance as the non-conformity measure, using ensemble approach with theoretical guarantees, and importantly, the method is inference time, which can be used for any LLM. We would for future work we would like to explore whether it can be used with other classes of models like multimodal LLMs, or maybe can it be used for more broader applications which are not related to medicine. So yeah, thank you for listening to this talk. I mean, you can visit my personal webpage, and or you can contact me by email if you have any questions. Thank you.